There was a question regarding the supply and demand. And the marine fuel. The company presented this in a conference here in Scotland last year. It was a Sulphur conference, and the presentation was about the marine fuel in Scotland by January 2015. And you will see here that there is a difference between the projection, the impact of the what will happen if the, let's say, the demand will start in 2020 or 2025. You see the different projections which exist for marine distilled demand according to when the new regulation will come into force, whether it will be 2020 or 2025. So depending on this, also the LNG requirements will be affected. So we expect that there could be a steep rise in the demand depending on, for the LNG bunkering, depending on the legislation and what the MEPC, which is scheduled for 2018, will decide. Let's go back to the presentation. See. So we saw the challenges. We discussed the specifics of the LNG. Let's see in general the options that the owners have in order to comply with the regulations. Here we have the owner priorities. Let's say usually we have usually the owners would like to minimize the cost, and that means the owner would like to minimize the structural cost, to optimize the design, to have an effective plan, to have an effective project management. The operational cost, this will include the running cost and the crew, insurance and maintenance, fuel, port and canal costs, terminal cost, handling, etc. What's this? The owner would like to, on the other hand, to maximize the revenue, and that means he would like to have an efficient operational management, a bunker management, crew management, and adaptation to new technology and regulation, environmental awareness, certification, training, and education. And the fuel cost is the most important expenditure item. So it can be a large portion of its expenses, and the owners should develop strategies by taking into consideration the changes in the fuel sector. So this is actually a game theory. So according to let's say the you have other stakeholders, and you should consider what the other stakeholders will do. And according to that, you will try to optimize your position at the next status of the market. See. So, if we could create a rather diagram of the different stakeholder priorities, it would look like that. We have the shipping industry on the one hand, it's one of the players, which requires safe, streamlined, fast, and economic solutions in accordance with the new environmental regulations. On the other hand, we have fuel and LNG providers. They would like to provide safety for the people and the assets, the protection of the LNG industry reputation, business in the downstream market. The other player are the ports, for which we need the provision of services to be effectively aligned with the existing operations. And then we have the bunker operators. For them, safety, maintaining business, and minimizing interruptions is the main aim. If we can put this in this rather diagram where we have safety, operational aspects, and commercial aspects, the priorities of the different stakeholders could look like this. So let's say with the dark blue line, the bunker gives the maximum weight to the operational factors, then to the commercial, and less to the safety. This could be one of the weightings. And so you see that the different stakeholders could, let's say, give different priorities and weightings to the different objectives. So regarding the fuel strategies, if you would like to operate in an ECA area, three are the main solutions which you have. The first one is to use your existing fuel. Use heavy fuel oil if you are an ocean-going vessel with scrubbers. The second solution is what the industry is doing actually right now. In many cases, use the fuel switching, use low sulfur fuel or other fuel near inside the SEC areas, and we will see what this causes and what's the outcome and the problems you may face. And then the LNG, which according to many of the let's say studies, is the best solution for a new built vessel, and we are going to explore in which framework and under which conditions this is the best way forward. This is the present condition. The sulfur content, we said it was 1.5. In 2010, it came down to 1%, and now it's 0.1% in 2015. This is the first solution. Let's say the one which has the minimum impact to the existing fuel selection. This is the scrubber. This is a typical dry SOx scrubber system. You can see the various components in this slide. We have the monitoring system here, the control cabinet, the bypass damper, the funnel in which this is placed, the selective catalyst system here, the supply silo, the absorber, the various piping, the pneumatic conveying, the flexible pipeline, and the various places where we have the connection to the external, let's say, supply of granulate. These abandonment technologies or end of pipe treatments are one solution. the use of the scrubber is sufficient in order to remove the SOx and reduce the also the PMs and to, let's say, acceptable levels. Then we have two main options: the selective catalytic reduction system, which is it look like this, and the exhaust gas recirculation, which actually takes some of the exhaust and gets them back into the combustion in order to improve the quality of the combustion and reduce uh, the, the SOx. Also, here we have uh, these systems. They could meet the 2015 SECA and Tier 3 ECA requirements and the Tier 3 NOx requirements. The values, if we would like to see the strengths, the weaknesses, and the open issues, the challenges of this combination, we should have a look at this slide where we have the strengths, which is the ECA compliance, the we don't need a new fuel tank, so the fuel logistics, the network we have, the suppliers is the same. We it's easier to retrofit and less expensive than the LNG fuel retrofit because it's a system which we apply at the end of the exhaust of the funnel. Uh, the weaknesses are that we have sludge reception facilities which we need, and this is a special substance with special treatment, and there are, let's say, the industry is not ready in order to get this sludge yet. There are a lot of questions for how this should be handled in the ports. Then we have space requirements because these systems take a lot of volume and the problem and a lot of weight. And the problem is that that weight is at the highest point, at the highest location on board the vessel, and that means that it has a significant impact to the stability. We need a large installation interface on board. There is a fuel penalty because there is a back pressure which is created at the exhaust, so the efficiency and the fuel consumption will be affected, and this means that we have operational costs. We have wash water criteria which we need to comply, and there are costs with the installation and the operation. Then we have power requirements due to the, let's say, the uh, the reduced efficiency and the CO2 emissions because the system is, let's say, the fuel is actually the same. The CO2 are not changing by the use of the scrubber, and we have to cope with the greenhouse gases emissions too. The discussions are around the performance on various engine loads, the integration with boilers, whether we can use them with boilers and other, let's say, equipment which is burning oil on board, and the corrosion which may be, let's say, created or due to its presence at the inside the fan. The scrubbers can be used for new builds and retrofits. They are preferred by long charterers. They, let's say, if we have fixed routes inside ECA areas, can be applied, and they are applicable to both deep sea and short sea applications. Here is an example. The first ferry, the Pride of Kent, is using this installation developed by Hamworthy and Wärtsilä. Uh, Hamworthy belongs to Wärtsilä. This is crystalline, and you can see the liquids, let's say, which we have, the substances which are circulating in the system. We have the seawater, we have wash water, the fresh air and exhaust gas with different colors in this system, and we see how the funnel changes has been modified in order to capture the SOx within this system. Here are a number of other examples where we have ro-ro vessels, old containers with different systems provided by different suppliers. We see that some of these involve quite large installations with up to 28 megawatts. Hybrid scrubbers from Wärtsilä and Hamworthy for the Ro-Ro Tamasis. And let's say there are also cruise vessels, the Liberty of the Seas, which uses a green tech system, and various others which you see here. These are just examples. There are various systems out there in the market. The principles can be slightly different. The principles are the same, but the system itself can be slightly different in order to improve, let's say, reliability, performance, efficiency, or minimize the penalty on the efficiency of the engine, and so on. So the other thing that someone can do in order to comply with the ECA requirements is to change the fuel type. We have the MGO. In general, the types of fuel which we have can be, let's say, distinguished in two large categories: the distillation residues, and the heavy fuel oil is the fuel derived by distillation. Residues often referred to as heavy fuel oil, which are heavier marine fuels compared with the viscosity and the sulfur content. We have also the fractional distillation products, which are the MGO and the MDO. The MGO stands for marine gas oil, and the MDO for marine diesel oil. And we have something which is a blend of them. This is the IFO, which is when the fuel is derived from the distillation residue mixed with fuel by fractional distillation, and this mixture is called intermediate fuel. So we can change the fuel, and these are the impacts in case we follow this strategy. We have some positives, which are the ECA compliance is possible. The safe and proven existing network is there. The recording scheme is established, and the crew is already familiar with this type of fuel. There is low investment requirement, initial investment requirement, but the problem is that we should expect an increase of the OPEX in the order of 30 to 40%. We have low flashpoint issues, and the fuel switching in some cases may cause a blackout of the engine. Challenges which are under discussion: the global availability and the price hike. The switch from to conventional low sulfur diesel oil has this impact. Let's say it's applicable to new buildings and to retrofits. So actually, there are minor things that we need to do in order to, let's say, make the vessel compatible to the new fuel type. Uh, this can be applied to any type of contract, anywhere. It's applicable to deep sea and salt sea shipping, and it's excellent for older vessels where additional investment is not possible in order to retrofit a scrubber or turn the vessel to LNG. And finally, the LNG. The LNG, as we said already, is environmental friendly fuel with low sulfur content. We have SOx and PM emissions which are negligible, as we have seen already. The NOx reduction can be 80 to 90% for four-stroke auto engines and 10 to 20% for two-stroke engines. We have less carbon emissions, about 20% than other fuels. The problem on if we select to go down the LNG, one of the problems is the storage. Because we have a liquid which needs to be at the atmospheric conditions, at the normal atmospheric conditions to minus 162 degrees. This means that we need special tanks, we need cryogenic tanks in order to make sure that the vessel, there is no, let's say, heat exchange with the environment, which will, let's say, increase the temperature. The liquid will start boiling, it will pass to the air, to the, let's say, it will become gas again, and in that case, the pressure inside the tank is going to increase a lot. Actually, the LNG will expand drastically when it becomes, let's say, gas, and this will be, let's say, disastrous for the whole installation. So we have the substances which are included, as we said, the constituent, the LNG is mainly methanol. We have other hydrocarbons and other substances such as nitrogen and the hydrogen sulfide and the carbon dioxide. Here is again the mixture which we have. Mainly it's methane, and that's why we have so low temperatures. In general, because the other hydrocarbons are more expensive than methane, we expect that let's say the impurity of the LNG will be low, because these let's say substances are more expensive, and someone who could invest in, let's say, because they have a different boiling point, they could be retracted during the regasification, let's say, the liquefaction. No, sorry, the turning from gas to liquid. So. The LNG is an aggressive greenhouse gas substance, and in that respect, we would like to avoid this escaping into the atmosphere. That means that if we have even the boil off which we have from the tanks, we would like to minimize this because it has an impact to the greenhouse effect. The methanol slip is something we have in four-stroke dual fuel engines, and we foresee that the methane slip will greatly be reduced in the future with the new, let's say, technology and the new um, forms and shapes of the chamber. Uh, we will manage to control it and minimize. The European Union believes that that LNG is the most promising alternative for short and long-term solutions to the emissions problem, and at least for the short sea shipping and other activities such as fishing and offshore services, uh, would like to consider the LNG as the main solution for the years to come. So in order to use the LNG, we have to find the engine which is going to burn the LNG, and in that respect, we need to come up with the right thermodynamic cycle which will provide the highest efficiency. We have two main options. This is the Otto and the diesel. With the Otto, the LNG may be used in the SECA as normal, and we can use the normal fuel oil for outside the SECA areas where the fuel gas is not available. The operating principle is based on the Otto cycle and the diesel cycle, and the ignition source is done during the LNG operation with using a small amount of oil, which is pilot fuel, and which is injected and ignited by the heat generated by the combustion and the compression and the combustion. The diesel cycle, this is the technology which is used when the gas is injected at high pressure. In some of these engines, we have 300 bars with pilot fuel. The engine can only use fuel oil or a mixture of gas and oil. And we have the single fuel gas engines where we use the Otto Miller cycle. And instead of pilot fuel, a rich gas air mixture is ignited in a combustion antechamber. This technology offers high efficiency and low emissions. And you can see here the ideal Otto cycle in the PV diagram. You are going to visit this more with Dr. Theodokatos. The investment which has to be done, if we compare, yeah.
Can we use dual fuel electric engines? Yes.
Electric.
Dual fuel electric engines.
You mean as electric generator?
Yes.
Yeah. This is an option. The thing is, what do we do inside the chamber? The electric, let's say, the electricity produced is instead of directly linked to the sun.
It's more efficient than single fuel, I think.
The overall.
Yeah.
It's over. Let's say if you have large changes of load, let's say the overall, the direct connection between the engine and the propeller is much better especially if you don't have a reduction gear. Okay, so in case you have a two-stroke engine, your efficiency for the transmission of power will be close to 0.96 or 98%. Using any kind of diesel electric propulsion in general, you are going to have more losses compared to the direct, let's say, transmission. The problem, the advantage is that you can use this power more you increase the flexibility of using the power created, generated on board. So that's the where you save. The transmission is you have more losses when you have transmission. Let's say you change from the
thermal loss.
no thermal. It's thermal losses due to the electrical losses in cables, power cables, and also you have to from the mechanical, let's say, energy, you have to convert this to electrical energy, and then you need another motor in order to make this again rotation. So the thing is that during this process you will have more losses than having a direct a shaft connecting directly the propeller to the main engine. But if you have, let's say, a lot of consumers on board, if you have large variations of your load, hotel load or whatever, then the diesel electric could provide you with some efficiency and cost savings. Okay?
Thank you.
So the scrubber here, with regards to investment, we have the installation, which needs a significant investment cost. The operational cost is marginally affected, and we have a slight increase in the fuel consumption, and we can have this to both retrofits and new vessels. We have examples from actual projects. With the fuel shifting, we can consider we can have a considerable increase in operational cost. There is a large gap between the price difference between the high fuel, the heavy fuel oil, and the MGO. The investment cost is not necessary, so we don't have to change many things on board the vessel, and the existing infrastructure is there in order to supply the MGO. And for the LNG, we have substantial reconstruction works in case of converting the vessel. We need to to retrofit the diesel engines, and we have to install new LNG tanks. The bunkering infrastructure investment is significant, and in that case, we need to first investigate whether the place where we are going to operate the vessel has this infrastructure. Otherwise, it will be very costly for the vessel to change its route in order to be, let's say, refueled. And it's let's say more attractive to new buildings, of course, with a high cost. The LNG price provides an important economic advantage if, let's say, it's let's say the gap between the LNG and the fuel increases. Some of these studies have been done when the fuel price was close to above actually $100 per barrel. So the prices now are much lower. So the gap between the LNG and the fuel has decreased a lot. This is a table where you can see the investment cost for alternative compliance strategies for retrofitting or for a new ship construction. You see here the compliance strategy, the retrofit, and the relevant cost for new builds. These are some figures. Of course, if you change the figures change from day to day. These are some rule of thumbs in order to understand, to have a first indication of what kind of costs are we talking about. So, for in case we have an MGO engine conversion with a scrubber and EGR, the retrofit cost is, let's say, you can calculate this giving this linear relationship according to the installed power. You have 180,000 US dollars plus 75 US dollars per kilowatt of power. So you can do easily the amounts in order to see uh, the total retrofit cost. For a new build, this cost is reduced, so it's the linear, let's say, approximation of the cost is 140,000 US dollars plus 63 US dollars per kilowatt. If we select the heavy fuel oil and the scrubber, uh, the with the selective catalytic reaction, this is gives us a cost of 600 US dollars per kilowatt. For a new build, this could increase to 2,200 US dollars per kilowatt, depending on the installation. For the LNG, if we have a four-stroke dual fuel engine and the LNG tanks, the cost is 800 US dollars per kilowatt, and for new builds, 1,600 US dollars per kilowatt. And in case we have the LNG two-stroke single high pressure dual fuel and the LNG tanks, we start with a cost of 700 US dollars per kilowatt. For a new build, this probably will increase size and more appropriate for the project. This number is double. And the LNG four-stroke spark ignition with the LNG tanks, the prices are pretty much the same. In this table, we see the investment cost for let's say, some examples of retrofits. For a RoRo for different types of vessels. These are thousands of euros. So using the retrofit for using the heavy fuel oil for the RoRo, this means cost of close to 2.3 million euros. For a coastal tanker, this will rise to 3.7, and for the container ship to 3.4. A large RoRo vessel will have a cost close to 10 to 9, let's say, million euros. With the LNG, the similar values. You see that the LNG is in all cases more expensive. We have 3.2 million for the RoRo, 4.8 for the coastal tanker, 4.8 for the container ship, and 12.6 for the large RoRo vessel. If we go to the new builds, the picture is again the same. The LNG in all cases is significantly, let's say, more expensive than the other solutions. Heavy fuel oil with scrubbers or MGO, change to MGO. The change to MGO, you see that in all cases is the most inexpensive solution with regard to investment, but obviously you have a very high running cost due to the fuel price. The operational expenses, the scrubber solution includes also additional operational costs. We can calculate this by the power output of the main engine times the time at sea in hours per year, and it's estimated that the specific consumption for using scrubbers is in the order of 0.0025 euros per kilowatt hour of the main engine. And we have then also a cost for the scrubber, which is 0.007 euros. Yeah.
Excuse me, I would like to ask you a question about the previous slide. I would like to ask you about the return of investment cost. For example, for the LNG, if a ship owner decides to make the retrofit into an existing vessel, the return of investment, what I'm trying to say is that
how many years you
yeah,
need in order to
how
break
many
even?
years?
Yeah, it depends. Usually, for let's say for any such an investment, 10 years would be let's say the preferable time in order to break even and start let's say gaining let's say having profit from this switch. There have been cases where they have according to the price of the fuel and the investment, the cost of buying the equipment. There have been cases with 5 years, let's say, break-even time. So it depends a lot on the status of the market, the kind of rates you can get. If you can get into a new market which the others cannot enter, if this LNG, as we saw very recently when we did a site visit in Finland, on board the Viking race, if the company is able to sell this idea as a new advanced technology, the state of the art, and it's you can attract more people, then obviously the return of the investment will be a lot higher. So it depends a lot on what kind of industry you are, what's the image of the company. If you can make other kinds of savings and having other benefits to the image to attract more people, let's say in general, LNG is very clean. We've been on board the Viking race and into the engine room. You cannot believe how clean the whole area is. It's like being in a museum. It's you don't understand that you are on board a vessel which operates 24/7.
Thank you.
So the thing is, if we select the heavy fuel oil to LNG, there is a decrease in the cargo area because we have to install the tanks. The operating costs is examined by a study done by DGL regarding a conversion of a container ship to which has the initial capacity of carrying 1,213, almost 100 TEUs, and this capacity was decreased by almost 50 boxes. So we had a 4% decrease of the capacity. In a container ship, the cargo space lost is of great importance, and other types of ships may have, let's say, no particular interest, as it may be easier to place the LNG tank in an area which will not affect the capacity. Of course, you have to consider that this new installation has some weight, And even if you are on board a tanker, like let's say the big Viking, the additional weight is going to reduce by an equal amount your carrying capacity. So if you are a displacement type vessel, or it uses all its maximum draft, then placing even on the deck such a tank could reduce your payload. Yep.
Yes, but if we retrofit a vessel from diesel to LNG, we don't need the tanks of oil. So
The tanks of oil, they are part of the hull. So
yes, but they are
even
empty.
even if you remove them, they are so much lighter than the structure you have in order to, let's say, place the LNG. The LNG tanks are very heavy, and the savings you have from removing some plates and their stiffeners are not compensating for the additional.
No, I'm not talking about the weight of the tank. I'm talking about the weight of the fuel.
The fuel is removed. You forget that. But the thing is that the tank itself, as a new equipment on board, is going to increase your weight.
Okay, and something else. As for the scrubber technology, you said that it increases the operational cost of the vessel. Is it possible to have to disconnect the scrubber in the open sea in order to reduce this loss?
If your engine, let's say, outside the SECA area,
Yes.
you could consider having something like that. But the thing is, will your this is applicable to SECA areas. So that's your main problem. If you operate, let's say, in the North Sea, from Belgium to Rosyth,
All time.
all time.
Okay, but if you go from Europe to US,
To US, then this is something you need to consider to find your time within the SECA areas and CBA. That's why we are saying you need the numbers in order to see the operation and see whether which solution is the best for you. Okay. And we have these are two key characteristics of the fuels we are comparing: the calorific value and the density. You see here the physical and the energy properties. We have the density and the specific energy for the MGO, the heavy fuel, and the LNG. As you said, the weight we have per cubic meter is half. But we have also to see the specific energy we have per ton, the gigajoules per ton specific energy here is the what we have for the LNG. And the supply, we need to bridge the shore and the sea, and now there are new guidelines and regulations which are finalized for the LNG fuel ships. The focus is on safety and let's say try to make sure that the normal operation of the vessel is not affected that much, especially when we are considering the use of LNG on board passenger vessels. Initially, there was an issue on whether when you have a passenger vessel, you should refuel with LNG with passengers on board or not. These things as confidence is building in and more and more refuelings have been conducted, especially with the Viking race. Initially, the requirement was that nobody should be in the area around the vessel and things like that. Now we will see the regulations and from the classification point of view. Now the Viking race, we've been on board with Mr. Christinas, is refueling during the loading and let's say embarkation disembarkation of passengers. So the Viking race, when it reaches Stockholm, the barge, the LNG barge comes close. They start the operation, the berthing of the barge next to the vessel. When the vessel is berths the key, at the same time, the passengers embark and disembark, the ones that get on board and the others who just arrived to their destination, and the bunkering takes place at the same time. This is the only way that they could stick with their very tight schedule, because they have to do everything within a certain time limit. In order to meet their schedule, they have to start going back to Helsinki. So the LNG and the safety should, let's say in general, the requirements should try to maximize the safety, but minimize the impact to the normal operation of the vessel. Otherwise, this would not be something the owner would like to have. If the whole schedule and the whole operation of the vessel is affected dramatically. Okay, so we have the LNG supply facilities. We have the onshore supply, the onshore mobile supply, or the offshore supply. Then we have the LNG bunkering facilities using shore to ship bunkering, truck to ship bunkering, or ship to ship bunkering. And through these methods, we may refuel the receiving ship. This is another graph where you can see the different alternatives. This is the logistics cycle of the LNG. We may have a large LNG terminal. This can actually, we can see here, we can pass this directly with a truck to the receiving vessel. We can have a bunker feeder vessel which will pass this to the vessel which needs refueling. We can have trucks which transfer the LNG to the intermediate terminal on shore, which can be a tank or a container, or offshore to a vessel or a barge, and this is then refueling barge, truck, or feeder vessel, or pipeline the vessel, the receiving vessel. We can have also, we can take gas from the grid, as we have here, it's a gas grid, and we can have a liquefaction plant, which will then pass this to some kind of intermediate terminal and through a pipeline, truck, or barge to the receiving vessel. The types of vessels which we have, let's say the applicability depends on the scale, and the scales of the let's say of the size of the bunkering we need, as defined by the Danish Maritime Agency (DMA), is considered we can distinguish it to large, medium, or small. And these are the large scale, where we have an import terminal with volumes more than 100,000 cubic meters. This could also be, let's say, an LNG carrier with the same capacity or reaching up to 266,000 cubic meters. We can have an intermediate scale, which could be an also storage, 10 to 10,000, the same for the LNG feeder vessel. And we can have a small scale requirement, which is an intermediate terminal with volumes less than 10,000 cubic meters. We can have an LNG bunker vessel with the same capacity, 2,000 to 10,000, or an LNG barge, which is the solution used for the Viking race, with volumes from 200 to 1,000 cubic meters. And if we are talking about a small scale requirement, then we can use trucks which have a capacity of 40 to 80 cubic meters. This is how it can be done. In this graph, you can see that this is the LNG fuel vessel. The three methods we have is the, as you see here, the sea-to-ship transfer, the STS, the truck-to-ship, TTS, the terminal pipeline to ship, the TPS, and you see the different solutions for bunkering the vessel. This is an example of the LNG truck filling the shore LNG tank at the Antwerp port. And this is an example, an illustration of ship-to-ship LNG bunkering, which, let's say, is something that in many cases the owners will, let's say, select in order to minimize the impact to the normal operation of the vessel. This is a truck-to-ship bunkering. And another innovative, let's say, solution is to use, let's say, plug-and-play solution with the LNG containers loaded onto a ro-ro vessel. This is a solution proposed by Levander in order to minimize the impact to ro-ro ships and, let's say, minimize the time it takes in order to refuel. You just take the empty LNG tanks and you place the new LNG tanks on board the vessel, and this is the fastest and very safe way of refueling. If we try to prioritize which is the best solution for the vessel, we can have such a map here. This is the mapping according to the ship type we have and the method which the owner will probably select for the fuel. You see the ship-to-ship transfer, the truck-to-ship, and the pipeline solution. You see here the various ship types, and you see with the red, it's the best solution according to the DMA's suitability analysis. You see that for a RoPax vessel, the ship-to-ship transfer is considered best. For tags, probably the truck-to-ship. It's also a matter of the quantity, the volume we need. The coastal tankers and bulk carriers, ship-to-ship, container feeders, ship-to-ship, the LNG feeders, ship-to-ship. For the LNG bunker vessel, the pipeline is the best. The LNG tanker, you see that also the pipeline is the best. The cargo, the Coast Guard, vessel is the transfer truck to ship. It's also a matter of size. For the OSV, the same. For a small passenger vessel, you can use either the truck or the pipeline. The large fishing vessel, the ship-to-ship, and for a very large crude carrier, the ship-to-ship. And here are the, let's say, a comparison between the merits and the demerits of the various solutions and why this map has been, let's say, it looks like that. The ship-to-ship transfer has the positive of being flexible. We have a high loading rate, a large bunkering volumes, and a sea accurate operation, which can widen, can expand the client reach. The problem is that we have high capex and opex because we need to convert the vessel, and we have also the requirements for the inspection, the operational costs in order to go to the location where the refueled vessel needs to be. And then we have the track to ship, which is flexible. We have low capex and opex, it's just a track. The low bunker volume capacity is a problem, and the low loading rate, as you understand, is another issue. Then we have the terminal pipeline to ship. The positive is high availability, high loading rate, large bunkering volumes, but the problems are the fixed bunkering location, so the vessel has to go to the location. The terminal space consumption, which also is an issue. And this is another issue. According to the bunkering solution, what kind of, let's say, time we need in hours. If we have a bunker vessel, the typical is 2.5 hours. The track is 1 hour. The time we need in between bunkering, and the pipeline we need only 1 hour. Then we have here the map where we can see the various ship segments and the average bunkering time in hours and the bunkering rate in cubic meters per hour. You see that for a small Ro-Ro or Ropax vessel, which is less than 180 meters, we need the average bunkering time is 1 hour, and the bunkering rate is 200 cubic meters per hour. For a large vessel, which is more than 180, we could go up to 2 hours, and the rate in this case could go up to 400 cubic meters per hour. For a small tanker, that means less than 25,000 deadweight, we can go up to 3 hours, and the rate could be 1,500 cubic meters. Large tankers from 25 to 200,000 deadweight tons, we can go up to 4 hours, and the rate is 2,000 cubic meters. The VLCCs, which are larger than 200,000 deadweight, we can go up to 6.7 hours, and the rate is 2,000. For small bulk carriers, less than 35,000 deadweight tons, 3 hours and 1,000 cubic meters. Large bulk carriers, they are again up to 2,000 cubic meters per hour. Small container ships with less than 2,000 TEUs, 3 hours and 1,000 cubic meters per hour. The large container ships with carrying 2 to 8,000, let's say with this large category at the upper end is the more comfortable, let's say, size. We need 4 hours and 2,000 cubic meters per hour, and for those very large container ships with carrying more than 8,000, we can go to 6 to 7 hours with 2,000 cubic meters per hour. Small general cargo, the same trend. You see, we start with 1,000. Here for the large cargo vessels with more than 5,000 deadweight, the more hours, but the bunkering rate remains the same. For fishing vessels, we need 3/4 of an hour and 60 cubic meters per hour, tax the same, and utility vessels the same. So we see the whole industry, what kind of rates we could use in order to, let's say, see what's the decide what's the best solution and how long it could take to refuel the vessel. So, as we said, the three scenarios: tank, truck, and ship to ship. The basic scenario is that we have no other cargo operation with no passengers in agreement with our instruments. But as we said, this has, let's say, has changed, and now the industry looks more confident for the use of LNG, let's say, in this during the normal operation of the vessel. The prices, this is very important. We can see how the prices have changed for gasoline, gas oil, and heavy fuel oil in Rotterdam. These prices are US dollars per barrel. You see the let's say the high increase we had back in 2008, and then due to that the collapse. So the prices fell to very low levels. They've reached, let's say, for the gas oil, close to $160 per barrel, and they collapsed to less than 60 within, let's say, a few months, in order to pick up and, let's say, go up. But now they have also reduced due to the situation in 2015 with the collapse of the oil prices in general. In order to convert the dollars per barrel of fuel oil, you should use this conversion factor. The $1 per barrel of fuel oil is almost $5.8 per million of BTU, and this is the way we can compare the price of oil with the let's say the LNG. And going to the LNG, you see now the LNG prices for the same interval, from the same period, from 1907 to 2014. You see that the Japan LNG prices have gone up, and this is the outcome of the vast requirement for LNG following the accident in the nuclear in the Fukushima nuclear power station. You can see also that the UK value is one of the it's lower than the one which you have the average German input price. You see it's higher. The UK one is lower, and you see the price in the US in the hub, which is let's say 3.6, so it's 4.5 dollars per million BTU. This is another graph showing the US dollars per million of BTU for the LNG in comparing the prices in China, Spain, Japan, and EU. And here you have UK. Here it's lower. Spain is higher. China is a lot higher, and Japan is even above. So you see how the prices, they are pretty much stable during this period. But obviously, you see here that they start being affected by the lower prices of fuel oil. That's it. Any questions? Let's see. Okay. Can you hear me now? Okay. Which is the question? Can you type it, Andrea? Oh, thank you, Giacomo. We have a problem with the return of let's say, picture and sound from the students, which we are going to solve by using a static IP. I think we will resolve this at some point. Why new building project now is affected by yeah, it depends on the size. Let's say the retrofit on the case study they done. Actually, they consider that they will use a smaller amount according to the. I think that yes, it is, but probably the size was different of the installation. I will pass the exact information from the study, and you will see why there was this difference. Okay. Okay. Thank you very much.